Welcome back to another exciting day of Organic Chemistry 1. Thanks for coming in. I know that I just gave you guys an exam and you're all probably pretty unhappy about that. I'm still trying to figure out what we're going to do with the final, and so we'll talk a little bit more about that at another time as that thought process sort of evolves in my mind. What I want to do today is finish up chapter 7 and then move into chapter 8. Like I said, I think I might throw chapter 9 as a online only kind of video because it's going to be strongly correlated and related to chapter 8. And so the reactions from chapter 9 are essentially the same reagents, the same reactions in chapter 8, except it's just going to, instead of operating on a double bond, it operates on a triple bond. And in very few cases, the outcome is the same or different. Essentially, it is the same. Depends on what happens. Once the reaction, there are some slight differences that you'll have to deal with, but I think that can be done again on your own. If you haven't been keeping up, I want to warn you right now. Things are really going to start to get deep, and you really need to kind of keep up. I know that the goal for everybody is to continue to progress in their education and to continue to move on with whatever program that they want to move on to. Several of you were talking about grad school and pharmacy school and all that stuff. And even though we've moved the withdrawal date to May, there is noise about giving you a voucher to take it again. So, if you withdrew and you took it in the summer, maybe that wouldn't put you too far behind. But the bottom line is, if you don't want to be behind, then you need to keep up, because even taking again in the summer is going to, stall some of that momentum that you have. And so let's go ahead and kind of get going with chapter 7. Where we left off was talking about how do we, now that we've gone through E1, we've gone through E2, we've gone through SN1, we've gone through SN2, how do we sort out which one of the different mechanisms might be in operation at any given point in time? And so let's switch over to the whiteboard, and then let's take a look at some of the considerations that you have to make in order to kind of sort that business out. All right, so essentially these are the three things that you have to consider when you look at a reaction as to what will actually be the operating mechanism and what will produce the major product. So the first thing, and these aren't necessarily in order of importance, but the first thing that you should do is you should take a look at the reagent. And by reagent, what we mean is, what's the function of the reagent? Is it a base? Is it a nucleophile? Does it do both? And if it does both, what's the relative strength of the things that it does? Essentially, what we're going to have is we're going to have 4 categories of reagent. You're going to have something that is essentially a strong base. You're going to have something that is a strong base, but also a strong nucleophile. You're going to have strong nucleophiles, and you're going to have a set of reagents that are weak bases and nucleophiles. Now, in Klein, he adds weak nucleophile here and weak base here, because technically, everything could sort of act as a nucleophile, and technically everything could sort of act as a base. But in general, the reason why I'm leaving this out is because once we talk about the things that are in those columns, that's all that you'll ever see them do, right? And so for all intents and purposes, yes, of course, a strong nucleophile is technically a weak base, but for whatever chemistry that we're going to come across, that's the only thing that's happening. And so one of the things that you should do is really become familiar with these reagents. And so in this strong base only column, you've got sodium hydride, and then you've got these two guys, DBN and DBU, and those stand for 1,5-diazabicyclo non-5-ene. Well, whatever. Let's draw a picture of it, since once they get complicated, names are kind of silly. Let's see here. Oh man, I'm really getting my 5-membered ring messed up here. Let's try one more time. Oh my goodness. Here we go. One of them lets DB in, and then the other one is got, it's like a heptane ring. The important part about me drawing them out is that I want you to tell me what the deal is with them. Why might they only act as bases? The nitrogens are going to be basic. There's going to be a lone pair on both of those nitrogens. If you take a look at that lone pair, it can't really act as a nucleophile because it's sterically hindered. All of this business here and all of this business here prevents it from acting as a nucleophile because of the steric hindrance around those things. And so at the end of the day, you're never really going to have to come across or really deal with the structures themselves. You're only going to see the names, DBN and DBU. And so that's what you should become familiar with in this case. And so there's really only 3 reagents that we want to deal with that are simply bases only. That's sodium hydride, DBN, and DBU. But you'll see those and you'll come across those. And so remember, they only act as bases. So if they only act as bases, what kind of reactions do they do? It's only going to be elimination reactions. And so and then specifically, it's typically only going to be E2 reactions. So those are the kinds of reactions that you're going to get into with those reagents. What about strong bases and strong nucleophiles? Well, if it's both a base and a nucleophile, then it can do both substitution and elimination, but you end up with essentially SN2 and E2. Those are the 2 types of reactions these reagents do. And again, I'm going to show you a chart in a second. But when I start to draw these out, think about what the commonality is between all of these things. So you've got hydroxide, methoxide. And we've also got ethoxide. Hopefully at this point, what you're seeing with all of those things is that all of them have a negative charge. So things that are negatively charged are going to react both as strong bases and strong nucleophiles. And so when it comes to, what I want to do is come over here to this column, a weak base and weak nucleophile, because they're very similar to those. They have both functions, basicity and nucleophilicity. They're very similar to the ones that I just wrote, but instead of being charged, they're the neutral versions of them. And so instead of doing SN1 and SN2 and E2 reactions, they do SN1 and E1 reactions. And remember, when I'm writing these things down, it's strictly only for the reagent. It's not considering anything about the substrate themselves. All right, so what about things that are just strong nucleophiles? And this is by far the longest list. They're going to do SN1 and SN2 reactions only, because if they're only nucleophiles, then they're only going to do substitution. And so these are the ones that you'll have to think about kind of memorizing, because again, they're not really, it's a longer list. 3 of them are certainly familiar: iodide, chloride, and bromide. Those are very common nucleophile onlys, the conjugate bases of very, very strong acids. But then it's also sulfur-containing species, no matter whether or not they're charged or neutral. Sulfur species don't really act as bases, and so they're going to be nucleophiles only. And so that's essentially a list of the different reagents that you're going to come across. You know, of course, there's going to be other things that you will see, especially in this category, because tertiary butoxide, which remember is that thing, and there are other bases. I don't actually know the name of this one, but it's even more sterically hindered. But both of these things would fall into this category. So this is by no means an exhaustive list of all the different possible reagents, but they're certainly the most common reagents. Okay, and so the next little bit is about the substrate. Once you've taken a look at the reagent, or remember, they're not in any particular order, so you really want to look at the reagent and the substrate together. You want to determine with the substrate, it's what are the possible or likely mechanisms, right? And so if I give you a substrate like this versus a substrate like this, there's really what I mean by looking at the substrate is kind of thinking about what mechanisms are coming into play. And so if I look at the substrate on the left, then I look at that leaving group and I say to myself, it's in a primary position. So what does that promote? Does a leaving group leaving in a primary position forming a primary carbocation favorable? I'd say to myself, not generally. And so that means it's not going to do, it won't do unimolecular reactions where the first step is forming a carbocation. It's most likely going to be bimolecular. And so that means E2 or SN2. What about this next one? Well, this position definitely looks like it's primary, but remember, it is primary, but it's also allylic. And so this one is definitely could easily form a resonance stabilized carbocation. So you think that probably this one would do unimolecular reactions. And so, you know, the same thing goes with if you're looking at other substrates, right? The problem comes up. So there's a tertiary substrate. So you should be thinking to yourself right there, unimolecular reactions. But here's the big problem. The problem is secondary substrates, right? Because with a secondary substrate, you've got a little bit of steric hindrance. So it kind of, it hinders bimolecular reactions because of that. But at the same time, it's only secondary. So when you think about forming a secondary carbocation, it's also not particularly energetically stable. And so that sort of is contraindicative of unimolecular reactions. So when you get to these secondary substrates, it really is going to be determined based on the reagents. And then remember, when it comes to reagents, there also is a secondary consideration of the solvent. And so when you come across a secondary substrate, the solvent choice could really make or break the particular mechanism that's going to produce the primary product. If I use a polar aprotic solvent, then it's going to be more likely to promote that SN2 reaction. But if I use a polar protic solvent, then it probably is going to produce a unimolecular reaction. And so those are the considerations to make when you get into it. Now, of course, if you have a secondary substrate and something that's only a strong base, then there's really only one operating mechanism, and that's E2. And so it won't matter. It's going to do an elimination reaction at that point. All right. So once you've decided, though, what the reagent is, what its strength is, and what the substrate is, and how those things come together to identify the most likely reaction or the major product, then the very last consideration that you have to make is, well, now that I've decided that it's going to be SN2, what are the regioselective or stereoselective considerations of that particular mechanism? So as I just mentioned in the example, if I have something for a secondary substrate, what if I do have a secondary substrate? I'll have to go get my I'll have to go take a quick break and get a charger. 1 second. So if you took something like this that was, you said, okay, it's going to be sodium hydroxide, but then I do DMSO. And so you say to yourself, sodium hydroxide is certainly a strong base, but it's also a strong nucleophile. And that means that it can act as both. Because the substrate is secondary, it's not promoting either particularly unimolecular or bimolecular reactions. And so it's not necessarily easy for me to sort out which one of those things is going to happen. But then I say, okay, but now I'm using the solvent as DMSO, and the DMSO is a polar aprotic solvent. And so I'd say to myself, okay, that really is going to promote the SN2 reaction as the primary product. Remember, there is going to be side products. And so now that I've decided all of that stuff, now I have to think about the regiochemical or stereochemical outcome. So if I want to think about the major product, then I would say to myself, well, the major product is going to have an inversion in the stereochemistry. So when I do a substitution, the hydrogen will come in front and the OH will come in back. But I know that there's also a minor product because substitution and elimination are in competition. And so I want to consider the same thing for the minor product. What's the regiochemical outcome? Because I'm going to form a double bond, and I can either form a double bond on this bond, or I can form a double bond on that bond. Well, which one's going to form? Is it going to be the Zaitsev or the Hofmann product? The more substituted or the least substituted product? And then I would say to myself, okay, hydroxide is a small, unhindered base. And so the predominant product is going to be the Zaitsev product. So if I were to write down the two products of the entire reaction, thinking about major and minor, I would say the major product is the substitution with the stereochemical outcome of stereochemical, I should say, more appropriately should say stereochemical, because stereoselective is just one particular consideration of stereochemistry. I said that OH is a small unhindered base. So as compared to something like tertiary butoxide, hydroxide promotes the more substituted product when I'm thinking about it in terms of elimination. But remember, at the end of the day, hydroxide is both a base and a strong nucleophile. So it really does both. And so it does come down to what's going on with the substrate. So if I want to take this even further, I could say there's an even really minor or a super minor product. And I'm certain that this happens just like this, that if I'm thinking about it in terms of elimination, the major product, of course, of this reaction is the substitution. The minor product is the elimination. Of the elimination products, the more predominant product is going to be the Zaitsev product, but certainly there's going to be some of this little other product made as well. And so this is putting all the pieces together for this particular reaction and how you do it. And so what I want to do at this point is to think about just kind of summarizing it in a chart. And of course, this same chart is in the slides. And so I want you to make sure that you are familiar with this slide, or at least familiar with this chart. So if it's a base, and it's a strong base, and remember, if in Klein, it's going to say strong base and weak nucleophile. But I'm going to put only strong base because essentially that's all you're going to see it do. Strong base, strong nucleophile, weak base and weak base and strong nucleophile, and then weak base, weak nucleophile. And so you should remember that the different reagents that we talked about on the previous, just a few minutes ago, have these properties. And so when you think about it, then the next thing to think about is the substrate. What is the type of substrate? And so you have primary, secondary, and tertiary substrates. And so they're going to make a little table like this. Okay, if it's a strong base and that's all it does, the mechanism will always be E2. It doesn't matter about the substrate. Okay. If it's a strong base and strong nucleophile, remember that that means with a strong nucleophile and strong base, it really is dependent on the substrate. So what I want to do is I want to say there's going to be a minor product, and the minor product is E2, but there's also going to be a major product, and the major product will be SN2. Now, of course, once you get to the substrate that's secondary, that distribution switches. All of a sudden, the major product becomes E2, and the minor product becomes SN2. But it's essentially the same two operating mechanisms in those columns. But once you get to a tertiary substrate, then really only E2 takes over. Okay. Now, what about weak base and strong nucleophile? Well, if you have a weak base and a strong nucleophile, then you essentially, for the primary substrate, you're only doing SN2 reactions. And that's true even for the secondary substrates. So if you do a reaction with something like sodium cyanide, and that's something that wasn't on our list, but it is, cyanide is a nucleophile only. It's a very, very, very weak base, and it only does nucleophilic reactions. And so if I did this on a secondary substrate, I'm only going to get substitution. The same is true if I do it on a tertiary substrate, but now instead of SN2, I get an SN1 reaction. All right, and so what happens if I use a tertiary substrate and it's a weak base and a weak nucleophile? Well, then what happens is I get a pretty even distribution of unimolecular reactions, E1 and SN1. And so now the question is, what happens if I use a weak base or weak nucleophile on either a primary or secondary substrate? And so this is what we want to say about that. You get a big mess, okay? You get a big mess of products. And so in the textbook and in the slides, Klein puts X's there. And I think the X's can be confusing because if you're not paying close attention, you might think to yourself, that means that there's not going to actually be any products there. And so that's not actually the case at all. What we're saying is you get to such a mess of different products, E1, SN1, SN2, and E2 products all mixed together in the same pot. What Klein says in the book is that it's not synthetically practical. But I don't want you to think that no chemistry happens, because certainly chemistry is happening. It's just a very big mess of distribution. So when you're doing a synthetic analysis, you probably won't invoke reactions in that category, but certainly there could be chemistry that's happening. And I think I've warned you already that I'm going to give you a problem that's over here in this category. And so in order for you to think about all the different mechanisms that could be in play. And so that's certainly coming up in the future. All right. So what I want to do right now is sort of like pause just for a second, because I want to switch gears. We're going to go into stereochemistry and regiochemistry. So hop into chat or something if you have any questions before I erase this. Okay. I'm going to try to keep that chart up there so it's at least somewhat readable. So what about these stereochemistry? Yeah, oh boy. What about the stereochemistry? Well, I think for the stereochemistry part, we need to remember what's happening. And again, this is always in the mechanism. If you know the mechanism, if you're very familiar with the mechanism, including the transition states, then you have a good idea for what's happening as far as stereochemistry and regioselectivity, because those considerations are already explained in the mechanism. All right. So what happens with SN2 when it comes to, and I'm going to put this together in one kind of chart. For regioselective and stereoselectivity, okay? And so what's the consideration for SN2? You get an inversion of stereochemistry. So that's what's going on with SN2. Why is that? The reason it is because it's a concerted mechanism. The nucleophilic attack happens at the same time as the loss of the leaving group. The nucleophile attacks the same carbon that the leaving group is on. And in order for that to happen all at once, the other groups that are attached that aren't leaving all come into a plane during the transition state and go flop from one side to the other because of backside attack. And so that's the consideration to be made for SN2. Okay. Well, what about E2? Well, remember, it depends on the base. If you use large base, you get Hofmann product. If you use small base, you get Zaitsev product. Okay. We say that this process is stereoselective, right? What does that mean? It means usually, so this is the regioselectivity. What about the stereoselectivity? In other words, once we've decided where the double bond is going to form, is it going to form the E or Z isomer? And so remember that usually the trans isomer is formed. Usually the less sterically hindered of the two possibilities will be the one that's formed. But what is the exception to that case? What is the exception to that case? If there's only one beta hydrogen, then you have to look at it. You have to consider. And this is when you have to do a conformational analysis. And so that when you think you're going to get into an E2 mechanism, you got a lot of considerations to make once you've decided that it's going to do an elimination. You have to first look at the size of the base to decide what the regioselective outcome is going to be. Is it a large bulky base leading you to the Hofmann product, or is it a small base leading you to the Zaitsev product? Once you've decided that, then you have to decide on what the stereochemical outcome is. Is there more than one beta hydrogen? If there is more than one beta hydrogen, then the less sterically hindered of the two isomers will usually form. If there's only one beta hydrogen, then you have to do a Newman projection, and you have to figure out which one it's going to be. Because remember, the transition state, the leaving group and the hydrogen that's doing the proton transfer has to be anti-paraplanar. And so in order to see that happening, you have to sort of line this up on a Newman projection to sort that out. Okay. What about SN1? All right. So what happens here? So in this case, we're going to form a carbocation first. So what's the regioselective and regiochemical and stereochemical outcome? Well, since it forms a carbocation in the intermediate, what happens usually is that there is a 50-50 racemic mixture, but remember there's a slight preference for inversion due to the proximity effect. Okay, but there's another consideration that you have to make, right? You also have to consider, once you've decided it's a unimolecular reaction, you have to think about, is there going to be any sort of carbocation rearrangement that's happening here? And so this is going to be true for any unimolecular reaction. Once you've decided that it's going to be unimolecular, you really do have to think about whether or not a more favorable carbocation can form through either a hydride or an alkyl shift. What about E1? Well, there's a little bit of good news with E1, and that's since you're doing elimination, regiochemistry doesn't really apply because it's always going to be Zaitsev. Okay. So Zaitsev is always favored over the Hofmann product. But the other problem is what about stereoselectivity? And so the same consideration is form. Remember that trans is preferred, but in this case, since you're forming an intermediate carbocation, you don't have to get into this consideration of, well, what about if there's only one beta hydrogen? Even if there is only one beta hydrogen, you're still going to be able to do you're still going to be able to form the more substituted alkene, because once you get into that, you're able to do free rotation. And so these are the considerations that you have to make once you get into this particular, once you get into a reaction where you don't necessarily know what the major product of the reaction is going to be. You have to make all of these considerations. All right, so let's just do a couple of practice problems to sort that out. I'll stop and see. So, so the question was no CA for E1. So what do you mean by CA? Type it out, please. No, you don't have to do a conformational analysis for E1. That's kind of the point there. Yeah, so that's what's going on. All right, so what about this? Here's an example. You have sodium ethoxide, and you have it in ethanol. So here we are. What are all the considerations? All right, this is how you would break it down. What's going on with the substrate? What's going on with the reagent? And then once you've decided which one of those, that combination of substrate and reagent, what mechanism does that lead you to? Then you want to consider the regioselective and stereoselective outcome. All right, so what are the reagents? The reagents that are listed on the arrow are sodium ethoxide and ethanol. So what does that mean? You've got sodium ethoxide, and so at this point, what you should know is that sodium isn't going to do any chemistry, and so you don't have to consider it. What is going to do chemistry is the ethoxide. And so what is that? Ethoxide is a strong base, but it's also a strong nucleophile. So that's starting to get to consideration. Okay, I can do either I can do either substitution or I can do elimination. But is there something else that's helping me out that's going to kind of determine which one would be more favored? Well, I do have a solvent as a secondary consideration, and that solvent is polar and protic because it's ethanol. Okay, so it's both polar and protic, and since it's polar and protic, I might want to think about necessarily not favoring substitution, right? Because what is the solvents that favor substitution? The solvents that favor substitution are going to be polar and aprotic. And that is especially in the consideration of the substrate. Well, what kind of substrate is it? It's a secondary substrate. So we already know that we're going to have a competing set of mechanisms with a secondary substrate. And what really determines what's going to happen is, in the presence of enough information, is what's the reagent and if there's something listed about the solvent. Well, in this case, with a secondary substrate, a strong base and a strong nucleophile with a polar protic solvent that's not necessarily promoting the substitution reaction, we're going to say, all right, the primary product will be the E2 reaction, and the minor product, so this is the major product, and the minor product will be the SN2 reaction. We've decided that based on all of the information provided. Once we've decided that the major product is elimination, and once we've decided that the minor product is SN2, now we have to think about regioselectivity or regiochemistry, and we have to think about stereochemistry. What's the regioselective outcome of the major product? Well, for the major product, we're going to say that it's Zaitsev, and it's Zaitsev because sodium ethoxide is a small, unhindered base. And so in the regioselective or the regiochemical consideration, the Zaitsev product will be predominant over the Hofmann product. So that means that the major product will have a double bond that forms between in a more substituted location between where the leaving group was and a beta hydrogen. Well, what's the minor product? The minor product will be the SN2 product, the substitution product. And because it's a substitution, now I have to think about the stereochemistry. Well, since it's SN2, I say to myself, there's inversion. And because there's inversion, that's going to make a difference on how I show the nucleophile connecting to the R group. And so that means I have to switch its location. If in the reagent, the leaving group was on the wedge, then that means I would put the nucleophile on the dash in the product. And so this is how we do an analysis of these two things. Okay. So let's do one more real quick so that we have another problem. Let's go through this next one a little bit faster. What if I have something like this? Sodium hydroxide. Okay. So what's the reagent in this case? Reagent is sodium hydroxide. Really, we're thinking about hydroxide. It's strong base, and it's a strong nucleophile. Well, what about the substrate? With the substrate, it's primary, secondary, or tertiary. Just pausing a beat because I think that there's some people that are, yeah, exactly. Thanks for being the one to pop that in. So there's some people in here that are thinking that it's a primary substrate. It's not. It's a secondary substrate. And I showed it this way to kind of illustrate that. That carbon there where the bromine is attached is connected to 1, 2 other carbons. It is a secondary substrate. So just, it's really important to be careful on the analysis and slow down. You're gonna have to slow down until you're really comfortable with all this. And so again, even from day one, you have to count carbons. If you're not counting carbons, you're not doing it right. And so it's a secondary substrate. And so we have to go from there. And so we're kind of in the same situation now. With a strong base and a strong nucleophile and a secondary substrate, we don't, it does appear, and that's what we're saying, is that showing bromine like this sort of makes it look like it's a primary substrate, because that looks an awful lot like this. But remember, it's not about the line to bromine, it's about how many carbons the carbon that bromine is attached to itself is attached to. In the case on the bottom, that carbon is only attached to this carbon, so this one is primary. But the bromine here is attached to, the carbon that it's attached to is attached to 2 other carbons. That's secondary. And so now what we're getting into in this situation is that a solvent isn't listed. And so we're just going to have to go on face value of what the chart we take a look at, or the thoughts that we make. So on face value, we're saying elimination is primary, substitution is secondary. And so what are the regioselective, what's the regioselective and stereoselective outcomes? Well, for the major elimination product, we're going to draw a double bond between one of the 2 carbons. Is it that one, or is it this one? Is it the one that's on the wedge? Well, in this case, it's a small base. Because it's small, it favors the Zaitsev product. So that means that we're going to put the double bond here. Now, the next question is how do I draw the next carbon? What's the stereoselective outcome? Do I draw the carbon like this, or do I draw the carbon like that? Remember, in this case, the trans isomer is favored because it's lower energy, less sterically hindered. So the less sterically hindered product will be favored. So the major elimination product, E2, is shown. This is the product that's formed. But what about the minor product? Remember, there's going to be an inversion in the stereochemistry. There isn't a regioselective outcome. Well, there is a regioselective outcome. The regioselective outcome is that I'm going to replace the leaving group, which was here, with the nucleophile, which is OH. But if I write this as CH3, have I inverted the stereochemistry? If I write that as CH3 and throw a hydrogen there, have I inverted the stereochemistry? And remember, you don't invert the stereochemistry until you switch 2 groups. So that's not how to write it. I want to make sure that I write it this way now. That's an inverted stereocenter. So be advised, but when you have stereochemistry that's not on a wedge or a dash, you have to kind of go back to chapter 5 and think about how do we draw the opposite stereo configuration. All right. Now, there's also a very minor product. And the very minor product would be the Hofmann elimination product. Okay. But really, these are the only 2 products I ever expect you to be able to identify, major and minor. Okay, and so there's just a couple of little things that we need to get into for the rest of this chapter. And so what I want to do is I want to just pause a beat have a sip of coffee, see if there's anybody that has any questions before we move on. All right. So the next two things in the chapter are about other substrates and alcohols. And other substrates really isn't a good name for this next section. The next section should really be called Tosylates, or better leaving groups. And so it involves something like this. We've already talked a little bit about the identity of an OH group and asking ourselves this question: is it a good leaving group? And the answer to this question is no, it's not a good leaving group. And so the problem with alcohols is that it's not a good leaving group, but they're easily, oh, so I'm sorry, let's go back. The question, how can you tell if it's a strong base or a weak nucleophile? And so there's a list of reagents that you can get into. Question is, how do you know if it's a strong base, weak nucleophile? There's a list of reagents, and if you just kind of go back into the video, you'll be able to see that list. That list is in the video, it's in the slides, and it's in the textbook. So you just have to be able to identify them as weak base, strong base, weak nucleophile, weak base, or both, or if there's a combination of that. And we spent a little bit of time talking about that at the beginning. So just go back through it. It's not a huge list, and you probably know most of the answers already on top of that. So when it comes to alcohols, they're not good leaving groups. They're not a good leaving group, but you can turn them into good leaving groups. So substitution like this is not favored. But you can make it a good leaving group. And so there's the next two sections in the chapter, the next two really talk about how do we make alcohols into good leaving groups. And so this is a topic that's going to come up over and over and over again in organic chemistry, so it deserves its own conversation. And so there's a whole different class of compounds called sulfonates. And a sulfonate is essentially something that is connected to a group that looks like this. That's a sulfonate group. And so R can be lots of different, this R prime or double prime can be lots of different things. It can be a CH3 group, it can be a benzate or a benzene group, or it can be a CF3 group. At the end of the day, there's lots of different things. What we commonly show is tosylate, a tosylate, Tosylates. And the tosylate looks like, it's the benzene version, so it looks like this. And so this is a very good leaving group. And the reason it's a very good leaving group is that when it leaves with its electrons, there is a high degree of resonance stability and resonance stabilization that's happening with this negative charge. You can show lots of different versions of how this thing can relocate its electrons. You can show that version. You could even have it do that. Let's see, what else could we do? We could go, maybe we could even go this way where we're having some charge move around that ring. And so there's a few different possibilities here. Maybe that one won't work. But at the very least, you've got resonance here and here. so I haven't actually thought about it one way or another as far as the benzene is concerned, but you definitely have resonance going into the sulfur and the doubly bound oxygen. So one of the first, what you don't what I haven't really said to you out loud yet is that you should, at this point, know lots of chemical reactions. So you're not aware of it because I haven't specifically said it up until this point, but you should know on the order of, like 10 or 12 different chemical reactions. We're not saying that you should have them memorized, but because you know E1, SN1, E2, and SN2, you should essentially know how to do these reactions. But there is a reaction that I want to show you that isn't necessarily obvious from the standpoint of E1 and SN1. And so it involves this. How do I take an OH group and turn it into a good leaving group? And TS stands for tosylate. Okay. All right, and so what you have here is you have a reaction that involves changing an OH group to a tosylate group. When you do that, you're maintaining the stereochemistry, and that's an important piece to remember. That what we're doing we don't need to know the mechanism of how a tosylate operates, but essentially what's happening with the tosylate is that it's attaching the TSCl is attacking the oxygen directly. So this attacks not the carbon. And so it retains stereochemistry. And so this is the first reaction that isn't necessarily tied to a mechanism that I've shown you that you have to know. And so it's kind of like at this point in time when I stop and say, look, you can brute force memorize reactions in organic chemistry 1. It's certainly possible. What is P4? I'm sorry. That's a good question. It's not P4. It's PY, and that stands for pyridine. And pyridine is a base. It's only a base. It's a nitrogenous aromatic base that looks like that. So that should answer your question there. So this is the first time that I say you can brute force memorize these reactions, although you shouldn't. You should really focus on mechanisms and reagents. But if you were to brute force memorize reactions, then you might want to draw yourself some index cards where you, on the front of one, you do something like this. And on the back, you do something like this. And so at this point, your students in this class, only about half of you think about mechanisms and reagents. The other half try to brute force memorize because that's what you're familiar with. You have time to switch from memorization to learning reagents and substrates and mechanisms if you kind of keep up with both at the same time. This is okay For Orgo 1, it's death in Orgo 2. In Orgo 1, you only have about 30 reactions to memorize. But in Orgo 2, you have almost 100. And so it's just not possible to brute force memorize reactions without having some connection to the mechanism and the identity of the reagents and what the reagents do. But since so many of my students do it this way, I want to make sure to stop and kind of give you a method for studying. You can make some index cards where you, on the front, you're testing yourself as to what the product is, and on the back, you're testing yourself as to what the reagent is. This way, it starts to get you used to thinking about reagents. Okay, and so this first reaction that's sort of not necessarily tied to a mechanism. And so what I want you to do is know this reaction so that you'll know how to make an OH group into something that is a good leaving group. Because once it's a good leaving group, then you can do different reactions with it. You can then do substitution and elimination reactions with it. Okay. So that's one version of what you can do with an alcohol. But now I want to talk, so if you have an alcohol like this, and your goal is to turn it into an alkyl halide, you can't just do sodium bromide. It's not possible. There's no reaction. You have to take a series of steps. Since hydroxide is not a good leaving group, you have to turn it into a good leaving group by reacting it with TSCl and pyridine. That will accomplish the goal of turning hydroxide into a good leaving group. Then once it is a good leaving group, you can react it with sodium bromide in a SN2 reaction to just replace the OH with the Br. So this is what it's useful for. At the end of the day, and this is the definite, in my opinion, this is the hard part about organic chemistry, is retrosynthetic analysis. And this is an example of a problem that would be a synthesis problem. How do you take one thing and turn it into something else? By far, the easiest of these problems are one-step synthesis problems. Something like this. If you're thinking about those index cards that I told you about, one side of those index cards are one-step synthesis problems. These are by far the easiest. It's when they get to be 1, 2, 3, 4, 5 steps down the road, that's when it becomes more complicated. Go ahead.
When you're writing what do you call the reagents, like you wrote sodium bromide, can't you write the TS chloride pyridine on top and then the sodium bromide on the bottom to show
Sure,
that
there's nothing wrong with doing this like this. Step 1, TSCl pyridine. Step 2, sodium bromide. And that's exactly what I'm doing. There's nothing wrong with that.
Yeah,
But
so it's in one step to write it's okay?
It's not one step though.
Well, I mean, like by the arrow, like at the arrow.
It's fine. It's fine. Yeah, it's fine. Yeah. But for this particular example, that wasn't helpful because I wanted to show people that there's an intermediate product that's involved. So this product here, where OH is now an OTS, and that makes it a good leaving group. And that's the point of me showing this particular structure. And so back to this idea of synthesis, the one-step synthesis is by far the easiest, right? Bromine is a good leaving group, so I can directly react it with sodium cyanide and perform this transformation. But if all of a sudden hydroxide is the what's on the substrate, then it's not a good leaving group, and I can't do it in one step. And so, like what was suggested, I would first have to turn it into a good leaving group, and then I can react it with sodium cyanide, and it would be a good, it would then perform the substitution reaction. All right, so that's one version of what we can do with alcohols. Another version is, how else can we turn it into a good leaving group? In other words, what happens if I react it with this? Is OH a good leaving group? The answer is no. So can it immediately do a substitution reaction with bromine? The answer to that question is no, it can't. But let's look at the reagent. Now, this reagent isn't necessarily, it's not a base at all, it's an acid. But alcohols do react with acids. And so there is something that we can show here, and we can show that when I have an alcohol and it interacts with an acid, I can form something that ends up being a good leaving group. Is water a good leaving group? And the answer to that question is absolutely. It's absolutely a good leaving group. And so now if I have the bromide hanging around, of course it is hanging around, now it can do the SN2 reaction. So this is SN2. It works the same way with SN1. If I have a tertiary alcohol and I react it with an acid, then I can still protonate the alcohol, turn it into water. Water is a good leaving group. In this case, the water, instead of being in a primary position, is in a tertiary position. So I can do a stepwise reaction that forms an intermediate carbocation. Of course, the bromide is still hanging around. So then it can directly attack the carbocation, and then I form the substituted product. So no problem with that. Okay. So that's an idea of how it does with substitution. Okay, so what I'm going to show you now is how alcohols work with elimination, but also this is an example of another reaction that you have to know that isn't necessarily tied to a mechanism that we've discussed yet. So it's going to be similar. It's going to involve one of those mechanisms, but not in its entirety. Or excuse me, the transformation is not entirely explained by just one of those mechanisms. It's only partially explained. So let's take this idea of a tertiary alcohol again. And let's react it with concentrated H2SO4. What we get here is an alkene plus water. How might this happen? Well, if I react this tertiary alcohol with concentrated H2SO4, then I've made a bunch of hydronium ion, which is the operating acid in aqueous solution. I can still make a good leaving group. And now what can happen? The leaving group can still leave. I can still form an intermediate carbocation. What's water, if you remember from that list? It's a weak base and a weak nucleophile. Well, I can show it acting as a nucleophile, and if I did show it acting as a nucleophile, I get right back there. So that's water as a nucleophile. And in fact, this reaction is an equilibrium reaction where the favored part, the side of the equilibrium that's favored is the formation of the alkene. We'll talk in the next chapter, we'll talk about how we can react an alkene with water. And it's essentially the exact same reaction, but instead of concentrated H2SO4, we use dilute H2SO4, because then in that case, we're adding extra water. And if we add extra water, which side of the reaction is favored reverses. So what do we got going on here? So once we've done this, now we've got water. We don't want water to act as a nucleophile because that just goes back to where we are. But now water can definitely act as also a weak base. And we form an alkene. So this was a proton transfer. Combined with these steps, which was a loss of a leaving group followed by a proton transfer. This is the E1 mechanism. And so you can still do elimination as well as substitution with alcohols, but you're going to have to make the alcohol into a good leaving group. It really depends on what you react it with. Reacting it with an acid like HBr produces one set of products, but reacting it with a acid like H2SO4 favors elimination products. All right, so I want to stop. I don't want to stop just yet. We got a few more minutes to go, but I want to stop right there because we're getting into the last part of this chapter now. Does anybody have any questions? All right. So what I'm going to do is just spend a few minutes talking about synthesis. I mentioned a second ago what's the essential heart of synthesis is taking something and transforming it into something else. And then your job is to figure out what's the series of steps that involves that transformation. And so let's kind of review at this point. We're not quite ready to start doing complicated synthesis problems, but you do have some basic reactions that you can work with. And it's really based on sort of the substrate. And so what I want to do is I want to think about what happens with a primary substrate and with the tertiary substrate. I'm going to leave out secondary substrate because all the same considerations apply. But remember, secondary substrates lead to a much greater mix of products, and it's really going to be determined based on the reagent and the solvent. And so you have to take a closer look. But here's some transformations that you can accomplish. If you have a primary alkyl halide, then you can react it with a strong nucleophile, and of course that promotes the SN2 reaction, and so you can turn it into an alcohol. You can react it with so that's a strong nucleophile and a strong base. You can react it with something that's only a strong nucleophile, and you can do only substitution reactions. But that's not the only strong nucleophile you know, or nucleophile only, but you also know sulfur-based nucleophiles, where you can substitute a sulfur. But it could also be a sulfur-based R group, where you would have SR, so a thiol ether. You could do this same reaction with OR groups, where you're replacing the BR with an OR. So these are all reactions that you know. Okay, but what happens if you react this with something that's a base only, like DBN or DBU or sodium hydride? Then you're going to form the alkene. Okay, so let me actually back that up. I want to make some room here. form the alkene. But once you know, once you get, so now that I've got some room, I'm going to go back to the alcohol, but I've also shown you how you can take an alcohol, react it with TSCl and pyridine, and you could make an OTS. What I didn't show you was how to take an OTS and turn it back into an alcohol. All you have to do is react it with sodium hydroxide. But now that OTS is a good leaving group, you can react it with a strong base, and you still get an alkene at the end of the day. You could do the same thing with a tertiary substrate, and you have some of the same considerations, right? Let's take this substrate like this. You could react it with a big bulky base like tertiary butoxide, and you'll get a Hofmann product. Or you can take it and react it with a small base like sodium hydroxide, and you get the Zaitsev product. You can take this thing, this tertiary alkyl halide, and you can react it with water, and it'll do an SN2, or excuse me, it'll do an SN1 substitution, and you can create an alcohol. But once you have an alcohol, you can also do a substitution, excuse me, not sodium bromide, with HBr, where you can protonate the water, and then it's a good leaving group. It'll leave, and then you can do a substitution. But you also know that once you have an alcohol, you can turn it into a double bond by using concentrated H2SO4. So see, these are some of the reactions that you should sort of have an idea for. Again, you can do TSCl and pyridine, and you can react this and turn it into a tosylate. Once you have a tosylate, there's other reactions that you can do in order to turn it into this product, right? And it depends on whether or not you use a bulky base or a small base. And so I know that I didn't say, here's a reaction that you have to know. Here's a reaction that you have to know. Here's a reaction that you have to know with all those SN1 and SN2 reactions. But the bottom line is that with knowing SN1, E1, E2, and SN2, you really do know a lot of different reactions. This by no means encompasses the entirety of all the possibilities of reactions that at this point in the game, you should be able to, you should know. And so this is where we're starting to get into some serious chemistry. And so I wanted to make sure that you kind of get an idea of how much information there is in chapter 7. And this really does sort of kind of get at it all. And so what I'll do is I'll say, you know, that's it for chapter 7. Let's just do one practice problem, kind of tying it all in together. And then we'll move on to chapter 8. So let's try to tie it all together. Let's try to put it all together. How could we make this from this? And so this is also a preview of what retrosynthetic analysis is like. So putting it all together, let's think about all the reactions that we know, and let's put all the pieces together that we know. And so I'm going to do the whole analysis to kind of put all the concepts down on the page and kind of think about what's going on. But at the end of the day, this is an example of retrosynthetic analysis. And what I mean by that is, start here and move back. What I tell students is that retrosynthetic analysis is a little bit of a leap of faith when it comes to chemistry, because the faith that you're trying to put into this is that if you can come up with whatever this is, and then think about how you could have made that from this, and think about how you could have made that C from B, the faith that you have is that at the end of the day, you will get back to whatever your original material is. Students often hesitate in doing retrosynthesis. They want to think forward. They want to go from A to B to C to D to the last material. And certainly that works sometimes. And I mean, in theory, it could work all the time. But at the end of the day, I think that retrosynthetic analysis really is a preferable method, because it does organize your thoughts and the reactions that you know in a much more concise way. What students often find uncomfortable is this sort of faith that I'm talking about, that if you just do it one step at a time, you will end up where you wanted to be, to where you wanted to be. And so let's try this. Let's put some information down as far as the substrate goes. And let's think about all the information that we have. Well, what's the substrate? The substrate is primary. That's one thing about the substrate that we know. What else do we know about the substrate? The OH is not, see if I can make it through here, not a good leaving group. So I might have to turn OH into a good leaving group in order to make this happen. What else do I know? I don't have, there's no stereochem to worry about because it's primary. I don't have to worry about that. Okay, what else do we know? There's no reagents listed, so we're going to have to come up with reagents. And so this really is sort of like about all the information that I can write down. I do know that if I'm going to if OH is not a good leaving group and I'm going to do one of these reactions, I will have to make it a good leaving group at some point. But let's think back. What could I have made this with? Well, this actually is the new group. I've made an ether here, and that is the new group. So how do I make ethers? Well, I need a nucleophile. What's the identity of the nucleophile? The identity of the nucleophile is the charged group that I added. Well, how do I get that in a pot? Well, I'm going to have to mix it with some sodium methoxide. I know that it did a substitution reaction, so maybe I want to make a secondary consideration that in order to promote the substitution reaction, I mixed it with a polar aprotic solvent. So now the next question is what was this thing? What was this thing that I reacted these reagents with in order to make this new group? Well, there was a good leaving group in the location of that ether group. But this is where this consideration that I made before comes in at. I started with an alcohol. So what was the identity of the good leaving group? Could it have been a tosylate? And I think the answer in this case is yeah, it certainly, well, it could have been water. But how could we do that? If we turn an alcohol into water, then there's only two options. There's HBr or there's H2SO4. But the HBr reaction leads to this substitution, which isn't necessarily a bad thing, right? This structure could be here. So let me actually make it a little bigger. Another possibility is this one. Right? Same reagents. That both of those reactions would produce the same product. Both of these boxes, box A and box B, would produce the product with this reaction, with the reaction of sodium methoxide and DMSO. So I could do that. So you're right. I could have reacted OH with HBr. That would have formed that one. But I could also have reacted it with TSCl in pyridine to do that, to do path A. And so that's a good, so I appreciate you bringing that up, because that is another sort of important part of the retrosynthetic analysis. There's very rarely only one right answer. No, the DMSO is not so the OCH3 doesn't react with the solvent. The DMSO is a polar aprotic solvent. Since I'm mixing a reagent, methoxide, which is a strong base and a strong nucleophile, with something that's a good leaving group, I want to promote the substitution reaction instead of the elimination reaction. So I use a polar aprotic solvent to do that. It would have been right had I just not listed the solvent. If I just didn't list the solvent, that would be okay as well. Like, that's still the, essentially the major product because of the substrate. And so what I'm going to do right now, I know that it's early, so we're 20 minutes early, but my iPad isn't going to make it. It's at 3%, and it's going to just shut off in about 4 minutes. And so I want to what I'll do is I'll just stop there and cut it off hard on chapter 7. That's it for chapter 7.